Next section we're going to look at today is section 2.3, existence and uniqueness of solutions to nonlinear equations. So we know that we have methods of finding solutions to these nonlinear equations. We mentioned them in the last video. They can be graphical, they could be numerical. There are lots of different ways you can find solutions. But sometimes it's nearly impossible to find a useful solution. So sometimes we have to convince ourselves that it's sufficient for us to, that a solution does exist. So if we can convince ourselves that a solution does exist and that it's unique, oftentimes that's really all we need to keep moving forward with the problem at hand. So how do we determine if there's a specific interval or a specific set of values on which our ODE has a solution, so it exists, and how do we know that it's unique? Or is there a specific interval on which it's unique? So the way we look at that is we consider an open rectangle in the Cartesian XY plane. So we say x is between the values of a and b, and y is between the values of c and d. And I've drawn a picture here to show you. So we're going to look at this little square, well, rectangle, it could be a square, of values and see if our ODE, and particularly we do initial value problems this way, if that initial value problem gives us a solution, it exists in this rectangle, and if it's unique. We may find that yes, our solution does exist and it is unique, and it may be even on the entire XY plane of real numbers. So it may exist for all values of x and y. It may be limited to values of x and y between very specific numbers, or it may that solution may only exist for that given initial condition for all real values of x and y, except for very specific relationship between x and y. So we're going to be looking at all of those kinds of problems. So our existence and uniqueness theorem from the text is theorem 2.3.1, and it states that if our function f is continuous on an open rectangle where x is between a and b and y is between c and d, and that rectangle contains our initial point, our initial condition, x naught, y naught, then the initial value problem, y prime equals a function of xy, and y of x naught equals y naught, our initial condition, it has at least one solution on some open subinterval of AB that contains x naught. So this is our existence. So this is where we're talking existence. So how do I know then that my solution that I say exists, how do I know if it's unique? Well, our theorem also says that if both f and its partial derivative with respect to y are continuous on our rectangle, then the initial value problem given in part A has a unique solution on some open subinterval of AB that contains x naught. So there's our uniqueness. So we have existence as part A, uniqueness as part B. So for existence, we're going to see where f of xy is continuous. And for b, we're going to see where the partial derivative of f with respect to x, or y, the partial derivative of f with respect to y is continuous. And that will limit us to where our solution is also unique. Before we move on to trying to find these values, I wanted to do a quick reminder of what partial derivatives are and how we find them. So remember, a partial derivative of a multivariable function f of xy with respect to x is written as del f del x, and it is the derivative of f of xy where we treat x as our function, well, we treat our function as a function of x alone, and y is treated like a constant. And analogously, the partial derivative of f of xy with respect to y, which is del f del y, is when we treat x like a constant and we find our derivative then with respect to just y. So I've given you a few functions here to try to find your partial derivative with respect to x and your partial derivative with respect to y as a good review. So let's look first at A, or 1, sorry, where it says we've got f of xy equals x squared y cubed. So if f of xy equals x squared y cubed, if we want to find the partial derivative of f with respect to x, which is del f del x, that would be 2x times y cubed. Remember, y cubed is just a constant. But now if we wanted to find the partial derivative of f with respect to y, or del f del y, we now treat x as a constant, so x squared stays there, and the derivative of y cubed would be 3y squared. So how does this change when we change our function a little bit? If I have x squared e to the y, then g, the partial derivative of g with respect to x, or del g del x, would be 2x e to the y. The partial derivative of g with respect to y, or del g del y, would be x squared e to the y, because the derivative of e to the y is just e to the y. And for our third one, we have this combined function here, x squared e to the 3x times the natural log of y. So when we take our partial derivative with respect to x, we're going to have to use the product rule. So let's find our partial derivative of f with respect to x. So now natural log of y is along just for the ride, but we need to find the derivative of x squared e to the 3x. And this is where we have to say it's the first times the derivative of the second plus the second times the derivative of the first. So we end up with the natural log of y times, let's see here, what all do we get? 3x squared e to the 3x plus 2e to the 3x. So if we really wanted to, we could pull out an e to the 3x and make it an e to the 3x, natural log of y times 3x squared plus 2. Makes it a little neater, but honestly, either one of these would work. So now let's try finding the derivative with respect to y. This one is going to be a lot easier because we get to leave the x squared e to the 3x alone because it's now a constant, times the derivative of natural log of y is just 1 over y. Now that we've discussed how to find existence and uniqueness of a solution and how to find the partial derivative of f with respect to y, let's try a few examples. So first things first, let's look at y prime equals x squared minus y squared over 1 plus x squared plus y squared, where we have y of x naught equals y naught. So our initial condition is x naught, y naught. So the first important thing to understand is that everything on the right here is my f of x, y. So our existence and uniqueness theorem tells us that for existence, we need to figure out where is this f of xy continuous. Well, because we just have a polynomial on the top and a polynomial on the bottom of this fraction, we really only need to be concerned with where the denominator could be equal to 0. Well, 1 plus x squared plus y squared is never going to be 0, right? It doesn't equal 0. It is never going to be 0. So we actually are not going to have any points of discontinuity here. So 1 plus x squared plus y squared will never be 0 for real valued x's and y's. Real valued x and y. So a solution exists for all real x and y. So that's kind of cool. So this one, it doesn't matter what x and y are. There is a solution to this ODE. Now, let's also talk uniqueness. is our solution that exists, is it also unique? Well, let's look at uniqueness. So we're going to need to find f sub y, right? Partial derivative of f with respect to y, del f del y. Well, this is fun because we have a function of y in the numerator and the denominator, so we're going to have to use the quotient rule. So we've got low, 1 plus x squared plus y squared, d high. Well, remember, we're doing this with respect to just y, so the x squared, its derivative is 0, so we're just left with negative 2y, minus high, x squared minus y squared, d low. Well, the derivative with respect to y of 1 is 0, of x squared is 0, and y squared is going to be 2y. And this is all over low squared, so 1 plus x squared plus y squared squared. Well, funny enough, we still have, in the numerator, we've still got a polynomial. Still is not going to require us to take square root of a negative number, and it's not going to have any kind of other points of discontinuity. So we still only have to worry about where am I dividing by 0. So where that happens is, again, where 1 plus x squared plus y squared squared is going to be equal to 0. But again, 1 plus x squared plus y squared will never be 0 for real valued x and y. So I say real valued because we could work in some, complex numbers here that we could probably figure out a way to turn this into 1 plus x squared plus y squared equaling 0, but we're not going in that direction. We're trying to figure out if we have a unique and a solution on a real number, in real numbers. So in this case, since 1 plus x squared plus y squared will never be 0 for real valued x and y, then we can say, right, that f sub y is continuous for, or that our solutions, so the solution is unique. And we would say then, therefore, that means that x naught, y naught exists and is unique for all real valued x and y. Let's try looking at another problem. So in this problem, we've got y prime equals x plus y over x minus y. So for uniqueness, we need to determine if there are any values for f of xy. And again, remember, x plus y over x minus y is our f of xy. We want to know, are there any points at which this function would be discontinuous? X plus y on the top is never going to lead us into a discontinuity, but x minus y on the bottom definitely can introduce some discontinuity. So we would be discontinuous, right? F is going to be discontinuous. There we go. F is discontinuous where x minus y equals 0, which is where x equals y. So in this case, we would say then that therefore solutions exist for all x naught, y naught, right? For all real, I should say, all real x naught, y naught, except where x equals y. So for uniqueness then, we have to look at the partial derivative of f with respect to y. Well, in this case, we're going to be looking at Quotient rule again. Low d high, well, which is just going to be 1 because it's with respect to y, minus high. D low is just going to be -1 because it's, again, still with respect to y, all over low squared. So we end up finding out that our denominator, x minus y, quantity squared, is the same discontinuity as the discontinuity we had for uniqueness. So here, we would say f sub y is discontinuous when, or where, I should say, x minus y equals 0 again, which also implies at x equals y. So therefore, we'd say each real valued x naught, y naught is unique, right? Except, right, except when or where x equals y. It's the same discontinuity that we had for the uniqueness. Or sorry, for the not the uniqueness, I wrote the same thing twice, didn't I? So for the existence, so let me change that. So this one is supposed to be existence. Sorry about that. I wrote it out right. I said they exist, but I labeled it wrong. So that will be existence. So we have the same discontinuity for existence and uniqueness, which seems pretty reasonable. So if the solutions can't exist where x equals y, then they can't be unique where x equals y as well. So it sounds reasonable to me. How about another one? Now on this one, we have y prime equals 10/3 x, y to the 2/5. And we have our initial value of y of x naught equals y naught. So we want to know for what points, x naught, y naught, does the theorem imply that the given problem has a solution? So this is speaking only to existence. So where does it exist? Well, are we ever going to be taking an even root of a negative number? No. Are we going to be dividing by 0? No. Do we have any asymptotes? No. So there are no limits to what x and y can be. So here we would say that f of x, y has no points of discontinuity, right? So all real valued x naught, y naught exist. So then, now, are they unique? So we know that these solutions exist, but we want to know for what initial conditions does the theorem imply that this problem has a unique solution on an interval that contains x naught. So here we need to find our partial derivative of f with respect to y. So in this case, we've still got the 10/3 and the x. And now we have to take the derivative of y to the 2/5. So that would be 2/5 y to the negative 3/5. Or, let's see, we would end up with 20x over 15 y to the 3/5. So we can simplify that to 4x over 3 y to the 3/5. So now the only place where we're going to have any discontinuity is where this denominator is 0. And that's only going to happen when x or when y is 0. So f sub y is discontinuous when 3y to the 3/5 equals 0, which implies y equals 0. So we would say then that there is a unique solution. So, so real valued x naught, y naught right? All real valued x naught, y naught are unique except when y, or where y equals 0. Let's look at one last example. So in this case, we were said, without solving the problem, determine an interval in which the solution to the given initial value problem is certain to exist. So we're not looking at uniqueness here. We're simply looking at existence. So that is where our f of xy, or in this case, f of ty, has any points of discontinuity is what we're looking for first. But what we can't do yet is just simply look at, because we have not solved for y prime yet. So we can't quite do this existence yet. So let's try solving first for y prime. So t minus 3 y prime is now going to equal 2t minus the natural log of t times y. So y prime here is now going to be 2t minus the natural log of t times y divided by t minus 3. So we have a couple of interesting requirements here to look at. First of all, we have to worry about this natural log of t. That implies here that t has to be greater than 0, because you can't take the natural log of a negative number, nor can you take the natural log of 0. The other point of discontinuity that we have to worry about is in the denominator. So we've got t minus 3. So the other point of discontinuity also be that t minus 3 can't be 0. So t cannot be 3. So now we know that t has to be between 0 and 3 or greater than 3. So we would say then that and we've got y of 1, 2. So does that fall into one of our intervals? It sure does. So what we say is that the given ODE, so the solutions, right, exist on the intervals t greater than 3, but less than, or sorry, greater than 0 and less than 3. So 0 is less than t is less than 3, and t is greater than 3. Right? And our given IVP, though, so our given initial condition is y of 1 equals 2. So that tells us that our x naught equals 1. So we have to decide which interval then is appropriate here. So, well, I guess it's not x naught, it's t naught. I misspoke. So t naught. So we need to figure out which of these two intervals then guarantees that we have a solution that exists where y of 1 equals 2. Well, it wouldn't be where t is greater than 3, because our t naught is 1. So in this case, we're saying our ODE is certain, right? Is certain to have a solution on the interval where t is between 0 and 3. And it's again simply because the initial condition we were given here is that t naught is 1. So that's how we fall into this interval. So I've given you a few problems to look at for homework, and they are these two. So without solving the problem, determine the interval of validity for the following initial value problem. And without solving the problem, determine the interval of validity for the following DE. So the interval of validity means uniqueness and existence both. So I know in example 4, we only had to do existence, but when it talks about the interval of validity, we're looking for existence and uniqueness.